Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will continue our discussions on compound compression with intercooling. Today we will cover multi-pressure systems, flash gas removal and flash intercooling. For the intercooling of a compressor, especially when air or some ideal gas is used, we have derived one equation that if the compressor is operating between two pressures P1 and P2, then we have derived the equation if intercooling is required, intercooling has to be done at a pressure under root P1, P2. This is P1 and this is P2 and it will come somewhere here. We also discuss that this is valid only for ideal gases where perfect intercooling is taking place. Perfect intercooling means after intercooling the temperature is equal to the initial temperature. But this does not happen in refrigeration system. First of all, refrigerant cannot be considered as an ideal gas, right. So, this expression can give us any value close to the intermediate optimum pressure, intermediate pressure, but this will not give us the exact intermediate pressure. But normally in refrigeration systems, ideal case the work done in both the compressors should be equal. But here what we do, we do not maintain exact value. For example, if Pi is coming approximately 3.6, we take as 4, right. So, we round it off to the higher values and normally it is seen that the intermediate pressure predicted by this equation is approximately 10 to 20% less than the intermediate pressure for a refrigeration system. So, in order to reduce this gap, investigators have suggested that instead of taking P1, P2, we should multiply this with T2 by T1. In some of the books, P1 is taken as PO, pressure of evaporator, and P2 is pressure of condenser, PK. Subscript K for condenser, O for evaporator. In that case, intermediate pressure is going to be equal to P1, P2, PK, PO and TK and TO. And these temperatures are absolute temperatures. Now, this intermediate pressure is close to the real value of intermediate pressure in multi-compression systems. Now, in multi-compression system where the compression takes place in 2 stage or more than 2 stage, the intercooling is done. After each stage, intercooling is done. Flash intercooling is done. Flash intercooling is preferred because for flash intercooling, we do not have to give extra arrangement for water line. Now, first of all, intercooling is required. It is clear that intercooling is required to minimize the work input to the compressor. And in case of ammonia, why I said in case of ammonia? Because what happens in case of, if we look at the pressure enthalpy diagram for any gas, the value of R22. So, value for gamma for R22 is 1.255, for R134A it is 1.158, for R717 it is 363. Now, if you look at these figures, then we can easily find that during a simple cycle, 2, 3, 4, when the compression is taking place and we are taking R134A as the working substance, then constant entropy line is going to be close to the saturation line, because T2 by T1 or here Tk by To, we can take this Tk or To. In some of the books it is written Th and Tl also. So Tk by To is equal to Pk by Po raised to power gamma minus 1 over gamma. So the moment we increase the value of gamma, this ratio increases. When this ratio increases means when T1 is fixed, temperature of the vapor coming from the evaporator is fixed, temperature of the vapor leaving the compressor increases. It means the slope of this curve reduces. So if we take a, for example, R134A, R134A, if the value of gamma is less, right? So this ratio will also be less. In that case, T2 will be somewhere here. This is for R134A. So R717 is ammonia. It is hydrofluorocarbon, and this is CH chlorohydrofluorocarbon. So this all I will discuss in details. We will take up the topic refrigerants, how the nomenclature is done. But let us focus on these numbers R22, R134A and R717. This is ammonia. So for ammonia, the value of gamma is 1.363. So Tk by To is equal to Pk by Po raised to power gamma minus 1 over gamma. So if we are increasing the value of gamma, when we are increasing the value of gamma, the value of this ratio is also increasing, and the value of Tk will increase because the value of To is constant. It means when the gamma is increased, this line will have less inclination and will end up somewhere here. Because superheating is taking place in this region, So if we take the case of ammonia, intercooling, it will be very effective. In comparison to the case of R134A, where the compression line is very close to the saturation line. That is why in small capacity units like domestic refrigerator you must have seen, there is a hermetically sealed compressor. In a hermetically sealed compressor, it is a sealed unit, welded unit in fact, and it has two wires coming out for the power supply, and there are two ports. The electricity is supplied through this wire to the motor, and motor and compressor, they run on the same shaft. The refrigerant which enters the compressor also used for cooling the winding of the motor, and the properties of refrigerant should be such that it does not harm the insulation of the coils of the motor. So for these type of applications, normally R134A and previously R12 was used. If we use any other refrigerant which has high value of gamma, there is a possibility that the proper cooling will not be there inside the hermetically sealed compressor and the windings will be burnt out. Now we will start with flash gas removal. In case of flash gas removal, what happens in a two pressure system? In a two pressure system, where here we can take P1 or PO and this is PK, it is a simple vapor compression refrigeration system. During expansion, flashing of refrigerant takes place. So suppose the refrigerant entering, suppose it is a low capacity plant and capillary tubes are used as expansion devices. So the refrigerant entering the capillary tube will be liquid, but slowly the flashing will take place. Okay, and after expansion to certain length, the amount of vapor becomes substantial, and if we remove this vapor, the idea is if we remove this vapor, because what is happening, this vapor will get expanded and again this vapor will be compressed. So, in order to avoid this, a flash gas removal system is provided in the system. So, if I draw an evaporator in a typical vapor compression system and there is a condenser. Between evaporator and condenser, a flash gas removal system is provided. Now, vapor emerging from the evaporator at state 1, right, and this vapor will get compressed and state 2. Now, we will have multi compression system, it is a multi compression system. So, it will, let us say it is 3. So, it is compressing, getting compressed and we are attaining state 3. Now, liquid refrigerant is coming from here, sorry, this is already 3 is already there. So, 4 we will take 5. At 3 liquid refrigerant is already there. So, liquid refrigerant is getting expanded in a expansion wall. After expansion, the flashing will take place or it will be a mixture of liquid and vapor. So, we will arrange one expansion here and after expansion the refrigerant will enter a flash chamber. It will not go to the evaporator, it will go to the flash chamber. Now, flash chamber is nothing but a vessel of relatively very large diameter, so that all the kinetic energy of the vapor is lost and stratification of the fluid takes place. I mean at the bottom position the liquid is accumulated and in the upper position the vapor is there. After this expansion, the liquid is remaining in the bottom side and vapor is remaining at the top side. This vapor is in saturation state at some intermediate pressure, it is in saturation state. Now, this vapor is taken away from here and mixed with the vapor coming from the compressor. So, we will say it is 6. Now, expansion has taken up to here, so this point is 6. This point is 3, 4, 6. So, this is, no, this point is 6. This point is 7. After expansion, it is entering the flash chamber. So, this point is 6. Now, here separation is taking place. Here it is pure liquid and here it is pure, saturated vapor. So, saturated vapor is coming here, that is state 7. And saturated liquid is remaining in the bottom of the flash chamber. Now, this vapor, saturated vapor is getting mixed with the superheated vapor. So, mixing of superheated vapor at 5 is taking place, both are at the same pressure, this has to be ensured. So, there is a regulatory mechanism also here, so that these two pressures are same. If they are not same, then imbalance in the system will take place. And mixing of these two vapors takes place. One vapor is saturated, another is superheated. So, mixture will be slightly superheated and we will get state 8. Now, in second stage, instead of compressing vapor at this state vapor will be compressed from this state. So, this state 8 state vapor will again go to the compressor. Now, this mixture available at state A will go to the another compressor and it will be compressed up to the state 9. As it is shown here, state A, it will be compressed and we will get the state 9. After the state 9, it will straight away go to the condenser, state 9 condenser, and it will be condensed to state 3. And remaining refrigerant which is available in flash chamber, the liquid refrigerant will go to the evaporator and it will be expanded. So, 6, it is 7, 8, 9, 10 and this is 11. So liquid refrigerant, it will go to the evaporator and it will get expanded there. Ten and 11 and then 11 to 1. Now during 10 to 11, suppose the part of the vapor is evaporated X fraction of the vapor is evaporated. So refrigerant available for this heat removal is only 1 minus X. However, this refrigerant is available at a relatively lower temperature. So this type of arrangement, if there is a multi-pressure system where more than one compressor is used, this type of arrangement is always preferred, or it is also recommended, because it saves the energy consumed by the compressor. Now flash intercooling, this is flash gas removal, but how intercooling can be done with the flash gas removal? We will draw another diagram for flash gas removal. Again there is a single evaporator and single compressor system. So evaporator and single condenser system. So there is one evaporator and one condenser. Vapor coming from the evaporator is going to a compressor. So state 1 to state 2. So vapor, this is saturated vapor. So saturated vapor coming from the evaporator is going to a compressor, state 2. Again we have a flash intercooler. Now flash gas removal arrangement is used as a flash intercooler. So in this flash intercooler, again the expansion is taking place and vapors are coming to flash gas chamber. This is a flash gas chamber and there is a stratification. Here we have vapor and the bottom side there is liquid. And this process can be shown somewhere here, right. So let us say this is state 3 and this is state 4. So this is state 3 and this is state 4. From state 3 the liquid refrigerant is available at state 3 and it is coming to the flash chamber. After expansion into the wall, in the flash chamber stratification of vapor takes place. Now for the purpose of intercooling, the vapor coming from compressor is bubbled through the flash chamber. In flash gas removal, it was connected with the vapor from the flash chamber. In that case, you are getting slightly desuperheated vapor at the entry of the second compressor. But here, the vapors coming from the compressor, they are bubbled through the liquid refrigerant. So any vapor emerging from here, if this vessel, the fluid in the vessel is in saturation state. So any vapor emerging from here will be saturated vapor. Now this is 5. So we are getting 5 here, and from 5 it goes to the compressor again 5, and after compression we get 6, and from 6 after second compressor, this is first compressor, in second compressor it goes to the condenser and condensation takes place. Now in this arrangement, the remaining vapor, suppose M1 is taken here, so 1 minus M1 will go to the evaporator and here also expansion will take place. So remaining part will go to the evaporator and refrigerating effect will be attained from, let us say 4, this is 5, 6, so 4 and 5 are same, 4, 6, 5, this is 5, this is 4, 5. So expansion is taking place here and the vapor is entering to the evaporator and refrigerating effect is attained. Now here in this case, in flash intercooling, the output of the compressor is sent to the flash chamber where this superheated vapor is mixed with the saturated vapor. Now in this course, because de-superheating of this vapor is taking place here. Some of the refrigerant will be evaporated. Some of the refrigerant will be evaporated in flash gas chamber, and that refrigerant will come into the second compressor. So, the mass flow rate in the second compressor will be higher than the mass flow rate in the first compressor. Now, if we take example of ammonia, ammonia has very high latent heat. So, if de-superheating is taking place in case of ammonia, small amount of ammonia will be evaporated. But if we take case of for example R134A, R130 ammonia has latent heat more than 6 to 7 times the latent heat of R134A. So, R134A substantial amount of vapor will be evaporated if de-superheating takes place in R134A. So, and that will increase the work of the compressor in second stage. So, this type of intercooling may not draw benefits in the case of R134A, but it is very useful for the refrigerant like ammonia, because ammonia has has high value of gamma. That is why level of superheating is, or degree of superheat is high in case of ammonia. And if this type of arrangement is made, flash intercooling type of arrangement is made, then a lot of energy can be saved in compression of refrigerant. Now, in order to this, in ammonia type of system, so water cooling is also done. Water cooling is also done because all the cooling cannot be done here. So, water cooling is also done. So, water cooling arrangement is also made. So, we get somewhere 2 dash and 2 dash goes to here. Then we get another stage 2 dash and the fluid available at 2 dash goes to the flash chamber. So, we have covered today the multi-pressure systems, flash gas removal system, how the flash gases are removed from the system, and flash intercooling system. So, because in a multi-stage system there are 2 types of cooling system, water intercooling system and flash intercooling system, and in case of ammonia refrigerant we can apply both type of systems. Now, in the next lecture we will start with multi-evaporator systems.